finished. The PBC, so to speak, the Physics Beyond Collider working group is still working and further investigating what can be done at CERN beyond colliders. And today, Joerg will tell us especially what can be done there to explore beyond the standard model physics. And I'm happy to give you the stage.
I should switch it on. So yeah, thank you very much for the kind introduction and also for the kind invitation. It's a pleasure to be here. And yeah, thank you all for coming despite what's going on. So thank you very much. Today I would like to give you a little bit of an impression what can be done to search for new physics that is not part of the standard model, and with the kind of tools and facilities that are available at CERN, and what kind of proposals are being discussed. Not all of them are being realized, but we will hopefully see at least a few of them being realized. And yeah, as Gunnar was already saying, this is a group that was originally invented to give input to the strategy, but now the idea is really to support new ideas for experiment. And actually Gunnar is now basically the head honcho from the experimental side. Okay, so let me just hopefully press the right button. No? I have the right button. It worked early on. Anyway, so the idea of physics beyond colliders is in large part about exploring for new physics. Be it also new physics beyond the standard model, but also in part new phenomena, understanding, for example, the strong interactions. But today I'd like to focus a little bit about the beyond the standard model physics aspect. Okay, a few years ago I found in a department a cup like this, and this is, I'm pressing the wrong button somehow. And now it will probably also work. There's something fundamentally wrong. So this is, as you may recognize, a variant of the standard model. It's kind of after spontaneous symmetry breaking, but the fundamentally wrong thing is this one. Nothing else. This is something that is completely wrong, and we know it. And we know it mostly from cosmology. So you've probably seen this plenty of times. By the way, please interrupt me at any time if you have questions, okay? So this is the pie chart of the universe, delineating what at least the universe on average is made of. And you have dark energy making most of it, a lot of dark matter, actually a fairly moderate amount of ordinary matter being whatever, nuclei, protons, electrons, and so on, and a little bit of neutrinos. Okay, so what do we know really about this kind of stuff? Well, dark energy is really the big unknown, I would say. Personally, this is just an opinion. I think this is probably one of the most difficult questions that we have to face. It's probably the most mysterious. It might be a cosmological constant, but it's really hard to explain why it's of this size, for example. So this is definitely not understood. And today I'll not talk much about dark energy anymore. Then the next big chunk is dark matter. We also are fairly sure, or very sure, that it's there. We have plenty of overlapping evidence from different directions, different scales. But we don't know what it is. We suspect it's particles, but that's all about that we know about dark matter to some degree. We roughly think that the mass is somewhere between 10 to the minus 20 electron volts. So that's about 25 orders of magnitude lighter than an electron. So really, really, really light particles. Or, well, it could also be not really particles, but objects with, say, a solar mass. So that's kind of 80 orders of magnitude of ignorance in what we know about dark matter. But we know something. We think it's kind of particle-like, so it's localizable objects to some degree. Anyway, I would still call it not very well understood. Neutrinos we have found, but neutrinos have a mass, and actually that's also fairly hard to understand. So explaining the origin and the size of this mass is, well, maybe not so well understood. Leaves our ordinary 5% perfectly described by the standard model. There's just one tiny little problem. If we think about cosmology, why do we actually have more baryons than antibaryons? Because we are all made out of matter and not antimatter. And, well, that's still a mystery, and it's not really possible to explain that properly in the standard model. So I would say that's also not very well understood. So the situation is actually great, because if you understand nothing, then there's plenty to be found. And that's, of course, what we want to do. That's what we do when we do research. So we should go and explore a little bit for new physics. And before ramping up the details a little bit, let me maybe do a little bit of a historical kind of analogy. So if you want to test a model, or if you want to go explore, you need a reason. Yeah? Experimentalists need to convince their students to actually do the hard work for many, many years with little rewards to actually, well, build an experiment. And for theorists, it's not much different. You have to do hard calculations and you want to look for them. So you need some motivation. And this is actually indeed where theorists mostly come in. They can provide a motivation. They have some big vision, sometimes of dubious kind, that tells you where to look for new physics. And for example, in the 16th century or so, people wanted to explore the southern hemisphere because that was a big unknown region. It's like a new energy region in physics. So people wanted to go and explore there. And then you need a theory that predicts something interesting there, because otherwise nobody is going to help you go there and nobody's going to fund you. So you need a theory. The theory is Terra Australis. The theorists you have asked, one of them at least is Gerardus Mercator. You see it in the uncanny fashion sense of a proper theorist. Anyway, so then you ask them for a theory, and well, here you have it. And well, you have some proper reasons. And then I have to say I didn't quite understand the theory, to be honest. But then you have to confidently say otherwise nothing would work. Yeah? And everybody else is, of course, completely wrong. But now comes the most important step. You have to draw an enticing map of where you want to go. And the map looked like this. This is Terra Australis, so the southern continent. You can look at it on the map. So this is, to a decent approximation, the rest of the world. And then you have Australia there. It looks rather enticing. Sometimes people have drawn some palm trees and whatever there. Look pretty. Of course, then you go and explore and you find something. You can draw on the validity of the theory your own conclusions, but something was found. Australia was actually found. So that's the good news. Doesn't quite look, it's not quite as big as the predicted one, but at least you discovered something. And that's, I think, always the end that is the most important part of it. So the message is, if you want to go on a trip of exploration, you should draw a map and ask yourself, what could you find? It's not guaranteed that you will find exactly this, but at least it gives you some motivation, but it also gives you some guide where to go and how to go there. Okay, so let's do that for new physics. So let's draw a map of new physics. And a first very sketchy version could look like this. it's motivated by the questions that you have to ask yourself, where is it actually worthwhile looking? And the answer is simple, where nobody looked before. And this map in particle physics is at least two-dimensional. We have tested the standard model in many directions, but you can ask which directions can we go? And one traditional direction is to go to higher energies. So for example, new physics could be hidden from our view because the new particles, and let's talk mostly about particles, are incredibly heavy. And as you know, if you want to make a heavier particle, you need a big machine like the LHC or perhaps something even bigger like the FCC that has enough energy in the collision to make such a heavy particle. And that has been a super successful direction in the last many, many years, so most recently with the discovery of the Higgs. But there actually could also be another reason why it was hard to discover the new physics. And that is that the new particles are simply extremely weakly coupled to our ordinary standard model particles. And then it's difficult because, well, we are only experimenting with ordinary standard model particles. And if the new particles are very weakly coupled, well, in any collision or any process, it's very unlikely that you make one of those new particles. And even if you make one, it's going to make a very hard to detect signature in your detector, so it's not easy to see. So if you go to very weak coupling with the standard model, it's also getting difficult. So what can you do there? So this is the other extreme. So you can, in that case, if you go far enough in the weak coupling region, you may not even have seen very, very light or even massless particles in some situations. So, but how can you test those? Well, for this direction, you need different types of experiments. Experiments that have, for example, a high precision, a high sensitivity, that experiment with plenty of particles so that you can, in a sense, test for small probabilities. So you have to have high intensity processes. And this is mostly the domain that we will focus on. It's a direction that also has historic precedent. For example, the neutrino was discovered much, much later than the electron, despite it being a lot lighter. And that's because it was very weakly coupled. And for the same reason, we haven't measured precisely all the properties of the neutrinos. It's not easy to experiment with neutrinos. So in that sense, this is also a direction that has been successful in the past. But I think over the last few years, there has been quite a bit of progress on developing new techniques, in particular in this direction. That said, essentially you can also go for a compromise. Say you have some moderately weakly coupled but fairly heavy particles, and then you need to adapt your experiments in a suitable way. So these are some potential experiments, and we'll come back to that a little bit later. Indeed, in a sense, in physics beyond colliders and a little bit its surroundings, this map is actually filled in a, well, quite interesting way with a lot of different experiments. The message here is it's very hard to build one experiment that covers everything. That's basically impossible because you need different techniques for different regions of this rough parameter space. Okay, so if you want to test weak couplings, you need something like precision or intensity. If you want to go for high masses, you need, in a sense, a lot of energy. And, well, there's always a compromise to be made. But the important thing is that different types of experiments complement each other. Okay, so that's the very first really rough map. But let's now go one step further and draw a concrete theory-inspired map. And the example particle I would like to use for most of today is so-called axions, or often also called axion-like particles, or if you wish, general pseudo-Goldstone bosons. As I said, there's more particles that can be tested. I'll come back briefly to them towards the end of the talk, but if you want to look, there's also a lot of information in this paper on the archive, for example. Okay, so what are these axions or axion-like particles? Well, the first thing you have to say, you start with a proper top-down theory motivation. You go to your string theory colleagues and ask them, do you have any axions at your, in your models? Well, if you ask the right ones, you have plenty of them. There are people claiming that there are hundreds of thousands of axions, but indeed you can go through models, and actually a huge class of extensions of the standard model have these kind of particles that have suitable properties, and why we'll see in a second, at least in a qualitative way. So let's see a little bit more closely what this kind of axions are, and to do this, I'll focus on their pseudo-Goldstone boson nature. So, what is a Goldstone boson? So, a Goldstone boson is a particle that arises when a symmetry is broken spontaneously. What does that mean? Well, typically we describe everything in terms of fields, and if you have a field and you excite the field, for example, all over space, you get a bigger and bigger field value. It's like, say, an electric field value that you can increase all over space. And this, of course, costs you energy. And for a typical field, you can draw then the amount of energy it costs you to excite this field by a certain amount. And the special thing about symmetries is that essentially a symmetric, a field that features a symmetry has the same energy for different field values, if you wish. So in this specific case of a so-called U1 symmetry, you can imagine the field having a real and an imaginary part, or you can imagine two real parts in a plane. And the energy basically the energy or the potential is rotation symmetric. So if you rotate the potential in the plane, the energy doesn't change. So for example, this field value has the same energy as this one and the same as this one. Now the interesting thing is you can have two different situations, and I've only drawn one here. You can have a situation where the potential looks something like this. It's rotationally symmetric, but at zero field value, the energy is higher than at some non-vanishing field value. And the idea of spontaneous symmetry breaking is now that, well, in the vacuum, this is the state of lowest energy. That's where you usually end up if you wait long enough with the system. You just let it relax to the state of lowest energy. Well, if you wait long enough and if you go to this vacuum, so to speak, your field value is actually not zero, because at zero, it has more energy than over here. So you actually, basically, your field rolls down its potential and acquires this field value over here. Which one you can't really predict, because as I mentioned, the field is rotationally symmetric, so all points along this ring have the same energy. But this actually has an interesting consequence. So you settle somewhere in one of those points. But now it becomes interesting, because if you now ask yourself, what would be the cheapest excitations of this vacuum? Well, if you move along this ring direction, well, these have all the same energy. So it doesn't cost you much energy to move along this ring. And that means if you go in this direction, you have a massless particle. It's only the kinetic energy that basically that costs you a little bit, but just exciting the field value in this direction doesn't cost you anything. It's only, in a sense, fluctuations that cost you energy. So in that sense, if you go along the ring, your potential just along this direction is completely flat, and this gives you a massless particle. Okay, so in that sense, if you move like this, potential remains completely flat. Okay, now, so in that sense, so this is a Goldstone boson. So in that sense, whenever you have this mechanism of a spontaneously broken symmetry, so when the minimum is not at the trivial field value, but really at some non-vanishing field value, then this symmetry is so-called spontaneously broken, and you get this prediction of a massless particle. And this is already a powerful prediction because it gives you something that is very light. It gives you a massless particle. And this is what we can access often in low-energy experiments. And it's a very generic thing. This happens whenever you have such a symmetry breaking. There's no way around it. Okay, it can happen, however, that the symmetry is not exact, but that your potential is slightly tilted. And if you then move along the ring direction, so to speak, well, it costs you a little bit of energy. You actually have a true minimum, so you feel you can now predict where you will end up in your vacuum, but excitations will also cost you a little bit of energy. But it's typically a small amount of energy. And that means the particle has a small mass. So that's the basic message. And the funny thing is, this mass may be much, much, much smaller than the scale by which you excite here the field, or you displace it from the zero field value. So in that sense, you get some interesting separation between a high energy scale and a low mass of your particle. Okay. So you can actually calculate a little bit what mass you get. It's fairly straightforward algebra. So if you tilt your potential a little bit by a scale lambda to the fourth, because it's an energy density, you can check, you get something like a cosine potential typically, because it lives on a ring. It has to be something like a cosine, and you can calculate its mass, and the mass turns out to be something like this tilting scale divided by the scale by which you displace the field from zero. And this is a truly interesting relation, because if your breaking scale is small, if your explicit symmetry breaking is small, and your tilting scale is large, you get an incredibly small mass. So you have a natural mechanism to generate very, very light particles. So in that sense, this is actually a fairly generic prediction in that sense. So you get a very small mass. Okay, and that's already one of the big theory messages. If you have a large scale of this spontaneous symmetry breaking, so a large displacement from zero, you typically, for these Goldstone bosons or pseudo-Goldstone bosons, you get a small mass. Now, this is one ingredient because we want to look at relatively low masses. The other ingredient is the coupling. Without going into too much detail, let me just mention that the typical couplings of such particles are, for example, couplings to two photons. So you have one of those axions or pseudo-Goldstone bosons here. So this is a light particle, and you couple to two photons. And the corresponding operator or Lagrangian term is over here, but the important bit is that the coupling constant, so the strength of the coupling, is suppressed by this scale of spontaneous symmetry breaking. And that holds for all the typical couplings of such a pseudo-Goldstone boson. Again, you have this kind of seesaw mechanism, if you wish. If you have a large scale of symmetry breaking, you get a small coupling. So in that sense, you have naturally light, but also naturally very weakly coupled particles. So the message here is if you get a large scale, you basically also get a small coupling. This is not necessarily desirable because then, of course, it's also harder to find. But it has at least the advantage of escaping detection. So let's now draw our map a little bit more concretely along these lines. It's still admittedly very sketchy and a bit generalized. So let's draw a map of these pseudo-Goldstone bosons and basically just draw a very large range of scales of different masses. So this is different masses. Here you have 1 electron volt. Here you have a tera electron volt. And here you have very tiny, whatever, 10 to the minus 21 electron volts. And instead of the coupling, I've just plotted here something like the scale of spontaneous symmetry breaking, or more precisely, 1 over the scale of spontaneous symmetry breaking. So for example, if you test something over here, you are probing a scale of 10 to the 6 GeV. And this is, in a sense, again, the advantage. If you are able to probe very, very weak couplings, say a coupling of this size along this line here, you're probing a scale of 10 to the 6 GeV, and that's, well, about 10 to the 3, a factor of 10 to the 3 higher than you directly probe at the LHC. Because there you have TeV scale energies in the collisions, and you probe TeV scale particles. But with this indirect probe, via this kind of suppressed coupling, you can often reach super high scales, orders of magnitude higher. The price to pay is you can only see this if it's associated with such a light particle. On top of that, you can see here now these gray regions, which are regions that are tested for specific coupling. So this is, for example, tested for the gluon coupling. This is tested for the photon coupling. You need slightly different techniques for each. And I've admittedly a bit carelessly just superimposed the two limits, which is not entirely fair, but gives a bit of an impression what scales can be probed. And to give you some idea in terms of both coupling and mass, LHC lives somewhere over here. So LHC really probes very heavy particles, but it only has access to moderately small couplings, simply because there's a finite number of collisions you can study. And then you have also very interesting fundamental scales, like, for example, the Planck scale, but you can see that some experiments are already touching scales as high as the Planck scale. And this is interesting also from a theory point of view, because I mentioned before that these axion-like particles or pseudo-Goldstone bosons are motivated from theory. So let's take another brief look. I'm also not a string theorist, so it's very, very qualitative, of how these particles are motivated in a theory like string theory. The important feature is that string theory lives in 10 dimensions. And that's obviously something that we do not see. So we have to get rid of all the extra dimensions that we do not see. We only have 3 plus 1. And the trick to do that is to compactify them or roll them up on some small scale. It's like a tube, which is, in a sense, two-dimensional. If you look from far away, it looks like a line. And you can do that with more dimensions in more directions, if you wish. So you have these extra dimensions, but they're typically made very, very small. But they're still dynamic in a sense. They can change. And this is a funny thing. So you can deform your space. For example, you can squish your tube, or you can stretch it, you can make it bigger. And all these deformations and changes in size and shape correspond to physical fields in our ordinary 3 plus 1 dimensions. So you have plenty of extra fields. And the funny thing is that it turns out that these fields exactly have properties like these very light. They're typically very hard to fix, and it's often very cheap to change the shape, for example, of a dimension or the size of a dimension. So they tend to be very light. They actually have underlying a symmetry structure similar to what we discussed. And they have properties very similar, and they typically come along with particles that have this axion-like nature or pseudo-Goldstone-like nature. So in that sense, string theory naturally predicts plenty of those axion and axion-like particles. Okay, so can we use this to make things a bit more concrete? Well, admittedly not so much, because if you ask a string theorist for a prediction in a certain space, you typically can cover the whole space with predictions if you do it right. You just have to ask nicely. But nevertheless, using the relations that we had before between the mass and the suppression scale, or the spontaneous symmetry breaking, you can draw a few lines that correspond to certain explicit symmetry breaking scales. For example, the QCD scale. This would be for the prototypical so-called QCD axion, that I don't want to go into detail. This would have an explicit breaking at the QCD scale, and this gives you a prediction that looks a little bit like this line over here. You can choose different scales and you get wildly different lines over here. But the only thing I would like to mention is that this explicit breaking, as it is actually true in QCD, so the theory of strong interaction, is actually typically very sensitive to the details of the coupling in a sense. Because if you look at the QCD scale, there is a physics explanation why one should write it in such a way, if you wish. It's the Planck scale times an exponential, because these explicit symmetry breaking effects are typically exponentially suppressed with the value of a small coupling constant. And then, because of this exponential, you can, of course, get wildly different scale, and that is what allows you to have a large region of parameter space here. Okay, I think I should speed up probably a little bit. How does physics beyond colliders essentially explore this kind of physics? And for this, I'll go through some of the experiments that we discuss in this context. Okay, and let's start at the lowest energies. One proposal is to search for an electric dipole moment of the proton. Just to give an aside, the absence of an electric dipole moment of the neutron or the proton is what motivated the original QCD axion, which is giving you this small, or the so-called strong CP problem. But the point is of this experiment that you can measure a proton electric dipole moment of the order of something like 10 to the minus 29 electron charges times centimeters. This admittedly already sounds like an incredibly small number. What would it be in the appropriate units? The appropriate units for a dipole moment of a proton is, well, it's a dipole moment. It's a length times a charge. Charges of quarks are order 1 electron charge, maybe a third or 2/3. And in the proton, you have space of about 1 Fermi to separate them. So the typical expectation would be 1 Fermi times an electron charge. If you look a little bit closer, there are a few more suppression factors, like a factor of 10 to the minus 3. But if you translate this, this is still more than 12 or 13 orders of magnitude smaller than you would naturally expect in a proton. And in that sense, you're testing, if you wish, the roundness of the proton, if you wish, that the charge distribution is equal in all directions to a level of 10 to the minus 12 or 13. And that's an incredible precision. The trick to do that is pretty similar to the so-called muon G-2 experiment. You essentially put your proton in an electric field and wait for the spin to precess. And experimentally, the trick is, for the muon, you do that in a storage ring. But there you are looking for a magnetic dipole moment, so you need magnetic fields. And that's a usual storage ring. Storage rings are keeping particles on the ring-like trajectory due to magnetic fields. The proposal here would be to build a purely electric storage ring made from not magnetic fields keeping things on track, but inward-looking electric fields. And people are confident that they can do it. There's a little bit of trick to get rid of backgrounds like magnetic moments. But the bottom line is that from the spin or the electric dipole moment precession, you would then, and what you measure as the spin precession, you can then conclude on the electric dipole moment with an incredible precision. And this is, of course, something that would be very suitable for CERN in a sense because, well, it would be a new type of storage ring and a new type of, well, if you wish, keeping particles on a circular trajectory. So what can you learn about this in our axion-like particle picture? Well, it turns out This combination here is what's called theta QCD. And as I mentioned, the dipole moment is something like theta QCD times 10 to the minus 16 electron charges times centimeters. And the funny thing is, such an experiment would be sensitive to both static and slowly oscillating dipole moment. So it could even be that the dipole moment is oscillating in time, which would arise in particular if this combination here, you are looking at the combination of the gluon coupling and our axion-like particle field value coupling to gluons. And this combination here, if this axion or axion-like particle is dark matter, it would oscillate. The energy or the particles that you make up your dark matter are stored in the oscillation of the field around its minimum. And then you would get an oscillating dipole moment. You would see it, and you could explore this region over here in this red area here. And I've plotted a fairly restrictive, you can even go further, dark matter region, natural dark matter region for these axion-like particles over here. So you would test really, really tiny couplings, possibly in the range of the Planck scale. So this is a very, very powerful probe of that. Okay, next type of experiment. This is an experiment looking for the coupling to two photons. And it's called, or it's proposed as the International Axion Observatory, or JAXO. And how does it work? Well, the experimental idea is you take a big fat magnet. This is a person here, so it's a really big magnet. And you point it at the sun. Why would that be something interesting to do? Well, if you have a coupling like this, that means you have a photon and another photon coupling to form an axion. And this is something that would happen gazillions of times in the sun, because in the sun you have photons, because it's hot, but you also have ions, which are essentially electromagnetic fields, which are just a different incarnation of photons. And then you produce these axions. But now comes the power of very weak coupling. These axions, once produced, they just go straight out of the sun because they're interacting so weakly that they do not scatter inside the sun. So whatever is between the production place, which is typically the center of the sun or close to the center of the sun, and us, you simply go through. Any wall or any plasma of the sun, you simply go through. And on the other side, you now produce or provide a magnetic field. This is the big fat magnet. And then out comes a photon. And this photon has the same energy as the axion, and typically the same energy as this photon over here. And that's a typical X-ray energy, because the sun has X-ray energies. And this is something you can extremely nicely detect. You can detect a photon a day, if you wish, in X-rays. So this is something where you can be really, really precise, that you're producing whatever, 10 to the 30 or so per second in the sun. So it's really a high flux. Okay, so if you do that, you can test an area like this. So you can now see the complementary. We are moving to higher masses, but we are not quite as sensitive. So we are actually going along this compromise line, if you wish. Okay, why would that be interesting? Well, for once, an important region lives somewhere here. I didn't put it all everywhere, but if you look more closely, this is the region that would be predicted for the QCD axion that is truly and strongly motivated by the absence of the neutron electric dipole moment. So this is an area that is touched upon here, but also people have observed an anomalous transparency of the universe towards gamma rays, and that could be explained in this lightly green region as well. So you're testing a significant part of interesting parameter space. You can go even further. You could make your axions yourself. You take a laser, you shine it through a magnetic field, and then you deliberately provide a wall, typically actually a mirror, and on the other side, you do the same reconversion process as in the so-called helioscope setup. So you do a light shining through a wall experiment, and it literally tries to do what the name suggests. You would have light, laser light, going through this wall and reappearing on the other side. This is what the ALPs experiment is currently doing, for example, in Hamburg, but this is something you could take to a completely new level if you take, for example, magnets that would be anyway built for a future accelerator. So this is always the kind of powerful technique or the technology that you're using from CERN, that you have these strong magnetic fields and suitable magnetic fields and potentially plenty of magnets. Okay, if you do this, you actually do not have quite the same mass range, but you could actually go even further down in coupling. And this is really not the end of it, and this is perhaps a little bit of aside from Physics Beyond Collider's advertisement with a couple of colleagues. I'm actually currently looking if it's possible to build such a light shining through wall experiment that can go in this direction, which would be essentially a sizable fraction of the QCD axion parameter space, under the assumption that you have some information on the axion mass. But if you know the mass, this type of experiment can really go powerfully far down here, and this would be a really nice, completely laboratory measurement of such a particle. In particular, it's nicely combined if you have a discovery in a dark matter experiment, combining it with such a measurement like this, you would really nail down that it is dark matter because you would measure both the coupling of the particle as well as the local density. And this is one thing you want to know if you want to establish something to be all of dark matter. You want to know that the local density is equal to what you expect from astrophysics or cosmology. And usual dark matter experiments can't by themselves establish that because they always measure only a coupling, product of a power of the coupling and the density. Okay, but let's go further in energy. Let's go, for example, for the so-called chip experiment. And this is now making a big jump in energy. It's using the SPS, the pre-accelerator of the LHC, which provides protons at 400 GeV. So now we are really making a jump from kilo electron volt X-rays to 400 GeV protons. And the idea is to do a so-called fixed target experiment. So the protons, impinge here, and then you try to detect some very weakly coupled particles or photons perhaps here. I'll show that in a second. There's at present the proposal SHIP, but there's also a combination of HIKE and shadows. Both can do this kind of beam dump physics, but HIKE can also do some kaon physics, which I'll return to in a second. Okay, so how does a serious picture of a fixed target experiment look like? Well, you have a high power beam, something like 10 to the 20 protons. This is a lot. This is really a lot of protons. You shoot them on a target. You have some stuff to shield everything, so all standard model particles are stopped here. And then you provide some decay volume and eventually a detector. So, for example, for a new particle, and let's immediately jump to the axion-like particle, your proton would come in here, make or radiate a photon, interact with some other photon from the material, and then you have your axion-like particle, which makes it through the stuff and decays into 2 photons, which you then detect. So it's pretty much like a light shining through wall experiment, just at higher energies. And this is, of course, where it gives you sensitivity. It's over here. So it's at much higher masses, but also, again, you follow a little bit this compromise line that higher masses are paid for by slightly less sensitivity. This is a very schematic plot. If you evaluate the sensitivities precisely for a model coupled to two photons, you rather get curves like this. And here you have the tested region, and ship and Hike can see particles of the order of a GeV in mass and coupling constants in the 10 to the minus 7, 10 to the minus 8 range. So it's fairly precise. Again, this is motivated because in a sizable fraction of this area, particles like this could provide a messenger particle to dark matter. They wouldn't be dark matters themselves, but they would be like the communicator between the standard model and the dark matter particles. And that's a fairly nicely motivated situation. There's also explanations of the G-2 deviation from the standard model value, which is perhaps the only more or less significant deviation from the standard model that we currently have. And this could be explained with particles in this region. Just to briefly point to that, G-2 is the deviation of the magnetic dipole moment. So it's now the magnetic dipole moment of the muon from its value basically predicted. If you just look at the Dirac equation, just look at relativistic quantum mechanics, these are the quantum field theory corrections, and they can be very, very precisely calculated. And, sorry, this is the calculation. And they are also very precisely measured. So this is really the small deviation. But now you see, those two do not quite agree, and there's a, 3 to 4 sigma discrepancy. And this is, again, something very interesting. First of all, you could have a new physics explanation, but you also have experimental progress, because the G-2 experiment at Fermilab is going on. It's measuring, and it is expected to improve the sensitivity. But funnily enough, theory is kind of stuck at the moment, and to make it better. So there's a discrepancy. Maybe lattice QCD can help and provide an interesting value. But you could also help yourself with some measurement, because you can measure to some degree the hadronic corrections, which are the problematic part of the theory calculation, the ones that you can't really calculate. And you measure them by essentially scattering muons and electrons. And the hadronic corrections are essentially when a photon splits into some hadrons, like pi plus, pi minus, or k plus, k minus. And you measure those by scattering muons and electrons very, very precisely. And then you can translate that into the G-2, which is a photon coupling to two muons. And these are the quantum corrections over here. So in that sense, muon E scattering may provide information here. And this is, again, one of those experiments proposed in PBC, and actually going forward, it's called the muon E experiment, which tries to measure this mu E scattering very precisely. Okay. So going one step further in energy, we can actually use LHC again in a different and novel way. Because if you look at it here, in collisions at the LHC, for example, this is ATLAS or CMS, these are really the highest energy collisions you have. But now you could still produce some weakly interacting long-lived particles. And they would not leave a trace in your detector, in your ATLAS or CMS detector, but it could be that they travel for a while and then decay. And to see these decays, which happen typically outside ATLAS or CMS, you would need a suitably placed, potentially also very big detector. And this is, for example, the Matusla proposal. It could be very simply instrumented, so it doesn't need to be super expensive, but still, Matusla is a very expensive proposal. A funny and also very clever idea is to realize that a lot of the lighter particles are produced forward, and in that direction, you need a much smaller detector, if you wish, to get the same kind of sensitivity. And this is actually already being realized. The phasor experiment is, or at least a small version of the phasor experiment, is installed at the LHC in some old tunnel and taking data and actually producing really new physics results for a relatively cheap price. So it's basically cost a couple of million, which for particle physics is really a low scale. Okay, you can do it a little bit better if you actually build a dedicated facility forward of one of the interaction points, ATLAS or CMS. And one proposal is the forward physics facility that could house actually a whole suite of experiments like phasor 2, but also experiments like Formosa or FLARE, and some neutrino experiments. Bottom line, this could explore really nicely and complement LHC to slightly lower masses in the GeV range. Again, showing the plot from earlier, for example, phasor and forward physics facility, for example, have sensitivity over here. Okay, I realize I'm probably, let me very, very briefly just mention that these axion-like particles were really only one example. There are a variety of proposals, or not proposals, it's actually, if you wish, a theory prediction that there are only a limited number of interactions or portals to the dark sector that you are likely to see. You can have particles like our axion-like particles, but you can also have particles that are more like a photon, more like a neutrino, more like a Higgs, or even more like a particle with a small electric charge. You can write down their interactions, and this is not the fundamental model, or it's not even supposed to be the fundamental model, but what we expect from theory grounds is that a broad range of underlying new physics models really fit and give signatures that are very similar to those predicted by these models. And the idea is, and this is an exercise that we have played in Physics Beyond Colliders, that a lot of these experiments are sensitive to a whole range of these different models. Okay, let me not go through all the details, there are plenty. Let me just, you can also do flavor tests. This is also an important area. You can test neutrinos. You can test also very interesting and creative, not necessarily directly physics beyond the standard model parts. And this is again let me just mention a couple of things here. With the technologies that are available at CERN, you can build, for example, something called the gamma factory, which would be a way to produce super high intensity gamma rays. And the trick to do that is you take the LHC, and instead of putting in protons, you put in something like a lead ion with one electron. So it's a super highly charged ion that you can accelerate to some incredible energy, but it still has one electron. And now the idea is, if you shoot a laser into the oncoming beam, so you're really shooting this laser onto the ions, the ion sees the laser photon, which maybe has an electron volt energy, extremely blue shifted. It's like the super Doppler effect, so to speak. And so this one electron or a couple of electron volt photon can now excite an X-ray transition. So you're exciting one of these really high energy transitions in this ion, so to speak. And the trick is, again, now once you have excited this atom, it de-excites again and emits a photon. But it emits it in the forward direction. So if you look now at it coming at you, it's again shifted by the relativistic gamma factor. And by that effect, you can increase the energy of the original laser photon by a factor of gamma squared, and gamma is about 5,000 or so for a suitable ion at the LHC. So you can, from an electron volt, make a high energy gamma ray. This could be very nice for material sciences, but it can also be used, for example, to produce axions or axion-like particles. So there are even both directions of applications. There are also experiments that explore something like the QCD phase transition, but this is something Gunnar can tell you probably much more about than I can. So let me finish up and thanking you for your patience. So I hope I have given you at least some idea that the exploration for new physics benefits both from high energy as well as high sensitivity, that you have experiments and you need experiments that complement each other in their sensitivity, and that we actually have the means to probe a lot of the interesting hints. And yeah, there are plenty more things to explore. Just to mention, there is more than BSM searches to PBC. There's QCD experiments, there's technological development, like this gamma factory, for example. But there are also QCD measurements that impact physics beyond the standard model. It can be this G-2 measurement by mu on E, but it can also be, for example, partron distribution functions for collider searches. And yeah, last comment, theory doesn't have to always be right. So for example, Columbus's theory about the distance wasn't quite correct. And for a theorist, not bad, factor of 2. Barely noticeable in the exponent. But if you're starving and hungry and thirsty, whatever, it might be hard for the experimentalist to actually make it. But he got kind of lucky. And yeah, with that, I would like to thank you very much.
Thank you very much, Joerg, for this very inspiring talk. I hope all the students take that last quote, go explore, go discover series. We have time for questions.
Hi, very interesting talk. I was a little bit surprised to see the lower end in the mass map that you have, because if you go to very, very low masses, shouldn't the axion behave like basically dark energy, be frozen?
At some point, yes.
So the gluon coupling shadow line goes all the way to 10 to the minus 24?
Yes. So you can start arguing that 10 to the minus 24 is probably more dark energy-like. Mm-hmm. This is kind of an intermediate range. I would say the proper dark matter region, maybe I should have cut it off, ends about at 10 to the minus 20. So this is where we have kind of good observational constraints that the mass shouldn't be lighter.
Okay.
Yeah.
And so the gluon coupling shadow is what experiment?
This one?
No,
this one?
The gray, yeah.
The gray one?
Yes.
This is a measurement of the neutron electric dipole moment, and they've done an analysis if they can see an oscillating signal in the measurement of the neutron electric dipole moment.
Right, but if you go to very low masses, that means that the time scale is really huge, right?
Yeah. Well, they have data from a couple of years, and 10 to the minus 20 electron volts is about a day. Oh. And they've basically, and this was in a sense their new analysis, they've plotted, so to speak, the time-stamped data and looked for oscillations in that. Okay. Was apparently very challenging to actually get all the different data sets together. Yeah.
Thanks. More questions? You have more questions? Okay.
So this idea of getting the photon to ultra-high energies, that sounds very nice. The only problem that I see with that is that because you are in the lab frame, the atom has to decay. I mean, it has a longer lifetime because of this gamma factor as well. So you have to choose the sort of decay that has a time that even with the gamma factor decays in the time that you want.
Yeah.
And that's possible.
Yeah, that's definitely possible because the gamma factor is small, is large, but not that large. It's a factor of a few thousand.
Ah, okay.
And indeed, in a sense, one of the good things is you may worry, does it happen often that I excite something, but you can actually tune it to be resonant. And then you have a huge cross-section, and basically you're using plenty of the photons you're basically shining into the beam, and it's a fairly efficient process. Mm-hmm. So they're fairly confident. They've done tests at SPS that they can store the beams, and they will test essentially the laser setups there as well. Funny thing is, to some degree, the experiment is actually more challenging at the SPS because the gamma factor is not high enough, and you need something like an ultraviolet laser to actually excite the right transitions. But LHC, it would be, better. In that sense, easier, but of course people don't like screwing with the LHC before having some tests.
Okay, thanks.
About the Methuselah experiment, if I remember correctly, is this one about long-lived particle, no? But do you have an estimate or where it should decay? So where to place this detector?
So, as I mentioned, there are several different proposals. Methuselah being perhaps the most ambitious one, perhaps being slightly too ambitious, admittedly, because the design calls for a 200 meter times 20 meter times 200 meter hall, which is a big hall. It's sparsely instrumented, so it's not as expensive as it sounds, but building just such a big hall is not cheap. So the drivers for this are to explore a new region in lifetimes. And if you plot lifetimes, there's a gap between what the Atlas and CMS can see and what would be very interesting in terms of particles decaying just before nuclei are formed in the universe, so slightly less than a few seconds. And this sets roughly the scales for these experiments. The nice thing you can do, and this is what people are perhaps more realistically now exploring, is if you move this thing somewhat closer, you can make do with a somewhat smaller detector. Because roughly speaking, what you need to cover is a certain solid angle or spatial angle. And that's directions people are looking with, which make it a bit more realistic, essentially.
Thanks.
Any more comments, questions? Well, then, thanks, Joerg, again. And I think the takeaway measure is that CERN is not only LHC, but many other exciting projects that ask for students to come and join the activities.
Absolutely. Thanks.